Hi, good morning. Welcome to our talk. It's already been introduced, but thank you for coming along. I'll get straight to it. The main aim of this talk is to share our experience investigating the domain of anti-cheat and to illustrate why it's such a fascinating area of study. We're going to share some of the sort of interesting defenses we found. In this context, cheats and cheaters are the attackers. Anti-cheats in games are the defenders. Do expect some cool defenses, a little look at sort of window kernel internals, and to learn why your computer is never as safe as when you're playing Fortnite. Do not expect comparisons of anti-cheat systems to spyware, bypasses of anti-cheat systems, or any development tips for cheats. Looking at the roadmap, we're going to have a little look at an introduction and a minor exploration of the world of game cheats. You're going to see some of our experiences investigating anti-cheat systems. We're going to go into the defenses we found that are particularly interesting for defense in general, not just in a game context. And then we're going to have a look at some takeaways, the impacts of anti-cheats, and the next battleground. Starting with an introduction, I'm Sam. I'm a PhD student at the University of Birmingham, UK. I do man-at-the-end attacks and reverse engineering. I also do a bit of game dev, but all my games are impossible to beat without cheating. Marius is an assistant professor. He mostly does baseband hacking and low-level stuff. Recently, he's hacked the RP2350, so if you want to check that out at DEF CON, he's talking about that. Tom is a professor at University of Birmingham. He's taught game hacking for years, and he's hacked some sort of small, lesser-known companies such as Apple Pay, Visa, and the Bank of America. Getting into the talk, first, we kind of need to set the scene. A harsh, cruel world which has created an even harsher, crueler people. So to survive here, you have to be tough, smart, and a little underhanded. This exists for software defense, and it's the world of cheats and anti-cheats. Then there's us. We're not necessarily anti-cheat developers or even game cheat developers by trade. We're an interested third party who's come to this harsh, cruel world to investigate the defenses that we've sort of observed being used here, and see what we can learn. There are a few good reasons why we study anti-cheat, which sort of the nature of which create this harsh environment. First, it's all-encompassing. We look at every single part of the system as a target. Hardware, firmware, networking, it's all in scope. And not only is the attacker model incredibly vast, it's also incredibly powerful. The attacker is the user, and so we see sort of really interesting ways of dealing with privileged threats from hypervisor, kernel, even like hardware. Some of these defenses are sort of mysterious. In many cases, they're sneaky and even underhanded. And the best reason to study anti-cheat is, of course, to play video games at work. When we're talking about anti-cheat, we are specifically talking about shooter games. We've picked these games because we sort of looked for a genre where there's the most titles deploying sort of good anti-cheat systems where they're interesting, so we can easily compare all of these titles. They're all raking in incredible amounts of money. They've got millions of monthly players, and as of now, they're all free. How do you cheat at games? So there's two real main cheat methods. The first is called an extrasensory perception, and this is your classic wall hack. It lets you see things you shouldn't see, and it requires access to the game memory, and we sort of show this in an app or an overlay. So think of people on a map, people through walls. Aimbots do the aiming or the shooting for you. Again, they require access to the game memory, so there's a bit of a theme here. And these are executed by artificial mouse clicks and movements. Before we get further into the talk, it's important to sort of acknowledge some of the prior work. There's been a few talks at Black Hat, DEF CON, etc. Everything from how to bypass current anti-cheat systems to exploiting World of Warcraft to make money. An important point we want to make is pretty much everything you might see in these talks no longer works. This is an incredibly fast-paced environment, and most of what's happened and has been documented has been patched very quickly. I'll pass over to Tom for the world of game cheats.
OK, so we wanted to know what's going on with cheats and how people use them. So we found a lot of websites selling cheats to gamers. So over 6 months, we monitored these sites, We looked at prices, we looked at uptime, and collected a big data set so we could see what was going on with them. These cheats are sold on a subscription model with people paying daily or monthly to cheat in these video games. On the whole, we found these to be quite well-run sites. They were reliable, they had user reviews, they accepted credit card payments. And we should note, in most of the world, cheats are completely legal. So for some of these companies, we could also find tax records and actually the addresses of the people who run them. Games companies have had some success suing these sites for copyright infringement, saying the cheat infringes the copyright of the game. But apart from that, these are generally legal companies. And one reason they're so well run is that there's a lot of money in selling these cheats. We found some cheats going up for $200 a month. That means these companies are making a lot of money, so they won't put malware on people's machines, they won't con people, because being a trusted cheat seller makes them so much more. And indeed, with a good Windows 0 day, based on our figures, a lot of cheaters could make more money by selling cheats than making malware or a bug bounty. So there really is a lot of money behind this, which explains why it's such an active area. To give you examples of uptime data, this is just cheats for the game Valorant. The green is when the cheat was working, and the red was when it wasn't. And what we can see is a cheat going up for sometimes just days before it's countered, and then the cheat developer gets straight to work, getting the cheat back up, getting around defenses. So this is much, much faster than the cycle of malware and antivirus. So this goes back to that harsh world environment sci-fi trope, which Sam talked about. The cycle of attack and defense in game cheats is much faster than anywhere else. So next, a quick primer on how Windows works and how game cheats work. So Windows security is based on having a really protected kernel. All of the operating system runs at the kernel level. This is signed by Microsoft. For anyone to run code, device drivers, for instance, they need to be inspected and signed. Other applications run at the user mode level, and anyone can run code here. So the game runs at the user mode level with the operating system high security functions signed at the kernel level. Cheats historically used to run at the user mode level too, and they'd call Windows API calls to ask the kernel to, for instance, give it access to the game's memory, reading and writing important values. In response to this, anti-cheat started running to also do the same, to make API calls, to try and intercept these attacks. And it became a bit of a slappy fight. Who could hook the function first? Who could detect the other first? In response, cheats and anti-cheats moved into the kernel. An anti-cheat running at the kernel level can intercept these calls and completely stop them. So with the anti-cheat signed by Microsoft, running in a privileged mode, it has a real advantage over cheat code running at the user level. That should have been game over. If Windows security was really as good as we might expect, with signed anti-cheats at the kernel level and cheats unprivileged at the user level, it should have been game over. But as we saw from all those websites, cheats are easily available. So it's not, the cheat developers have found a way around this defense to get their cheats working. I'll hand over.
Thank you. So before coming to our technical findings, I want to take you on a little journey. And this journey is our experience while carrying out this research, while investigating anti-cheats and anti-cheat systems. And for this, I really want to first do a small shout out to all the cheat forums out there, right? They're really the best and the worst source of information for this kind of research. They can provide us at the start with good game offsets where we really get our reverse engineering kick started. They can give us guides, like they tell us how certain anti-cheats may work at a given time. And then, of course, they also give like some interesting comments, like, is soldering the DMA to RAM slots helping us for cheating? I don't know, we haven't tried yet. But no, overall, cheat forums are a great resource. Now, when we started looking at anti-cheat systems, we felt a little bit like prodding the bear, right? In a nutshell, we are trying to analyze a piece of software which, by definition, does not want to be analyzed. And for this, a lot of different things happened. Of course, we needed to reverse engineer and stare at assembly. Now, maybe when we wanted to go for debugging, we needed to attach ourselves to the hypervisor to do debugging from the outside, and we got blocked on the way, and we needed to play a bit of cat and mouse to get there. We would experience crashes forced by the anti-cheat systems, and not only crashes, the anti-cheat systems would also falsify or fake the information in the crash dump, making our life harder. When trying to attach a debugger to an anti-cheat, we may get funny messages from the developers, like, hello, it's Vanguard, who dis? Right? Just to mess a little bit with us, maybe to make our day more sweet or make it a little bit more difficult to reverse the anti-cheat. In this spirit, also fake symbol files are a thing. Looking at the Vanguard anti-cheat, we get a link in the symbols to an image showing the development team of this anti-cheat. And besides all of this, we also had other experiences, right? We were poking at these things, and they did not really like it. We got banned from multiple games, right? So here we have one ban screen, it goes on. Like, we really, really got banned a lot. And not only this, beyond being banned, the anti-cheat systems would occasionally go a step farther. They would crash our system. So we would be confronted with nice blue screens and having to continue our odyssey. Some of the bans were also tied to our hardware ID, so we could not even create a different account and try to reanalyze the game. So we went down the only reasonable road here. We turned to hardware hacking. So we started to desolder motherboard chips, to change our hardware IDs, just to be able to keep playing and keep analyzing. We changed information on some DIMM slots. So there was really a lot of stuff going on. And overall, at some points, we really had the feeling, why? Why are we doing this to ourselves? Why we are still here? Now the answer is to be here, to be able to share with you our cool findings. So the treasure chest of defenses which anti-cheats brings to us. And before starting talking about one particular defense, we really want to highlight that all the defenses use some combinations of defenses which are already out there, right? We have registered callback, we have signature scanning, anti-debug techniques, TPM usage, instruction misalignment. So all of these techniques used by anti-cheats in itself are known, but put together in a pot like this to a complexity, we have not seen it in different systems so far. Let's start looking at one of the anti-cheat measures we can analyze, or we did analyze, which is mitigating bring your own vulnerable driver styles of attack. So coming back to the Windows security module, which Tom also talked about, right? All code running in the kernel should be signed. And to enforce this is Windows checks that all code loaded into the kernel via normal APIs is signed. This, of course, is not the same, right? There may be other ways to get code into the kernel, not using the normal APIs. And this is where bring your own vulnerable driver as technique comes in as a tag technique. So legitimate drivers which a user of a system can load may contain bugs and vulnerabilities. Now, attackers can exploit these and use this as entry vector to get code into the kernel. And as this unsigned code is now loaded in the kernel and running, it would allow us, for instance, to develop cheats or try similar things. This is, of course, not great, right? This is where the battle between cheats and anti-cheats on this harsh planet goes on. We now change the battle stage to be the Windows kernel. And interestingly, it's not only anti-cheats which are using these kind of techniques. In recent years, like since 2023 really, but also before, bring your own vulnerable driver as a tag technique became more and more popular for malware and especially ransomware. Let's look into this in a little bit more detail. We have here a timeline, and just as an example, we have the Gigabyte driver, gpci driver.sys, And in December 2018, an arbitrary kernel read-write was found with a public CVE and posted online. Now, 5 months later, in May 2019, we see the Robinhood ransomware using this vulnerability to get leverage. And then, only quite a while later, shortly before the start of 2020, we see first ADRs and AVs picking up on this. Right here we see Checkpoint Sandblast detecting Robinhood, and we also see Sophos EDR being specifically tailored to block this driver, this vulnerable driver used here. Now, there's a second aspect to the story, or a second timeline, which is the timeline of anti-cheat systems and of cheat developers. Only 8 days after the CVE was posted, we can see that the GPCI driver.this appears on unknown cheat forums. That's the name of the forum. And the cheat community was actively discussing this vulnerability. And in a matter of days, first cheats came up using this. And as a response, already in May 2019, battle-I anti-cheat blocks the driver from being loaded. So we see more than a year advantage in the anti-cheat field than what we see, for instance, with the Sophos EDR in time of response to this particular threat. And this is not the only case, right? We could go on with additional samples of malware, like we have Trojan.downloader here, like this is all around 2022, when bring your own vulnerable driver became really big in the news because it was used in a lot of different attacks. So Blackbyte here, Scattered Spider, and something from APT41, all of them were using some sort of vulnerable driver to get code into the Windows kernel to leverage their malware and ransomware. Anti-cheat systems blocked all of these 4 vulnerable drivers already years ahead, like in 2020. So the main takeaway which we want to give here is not that EDR and antivirus are not working, it's just that cheats and anti-cheats move way faster than malware and EDRs in this attack and defense game. So again, we are on this harsh planet where soldiers develop very fast. How do anti-cheats stop bring your own vulnerable driver? It's mostly a mix of two methods. One is load time prevention. So the anti-cheat will just try to block the driver from being loaded altogether. Or runtime detection by signature scanning of the memory during runtime to make sure these drivers are not in place. Now, let's look at other ways how anti-cheats harden the Windows kernel.
Okay, so we've seen some sort of simple methods of preventing drivers, but there's 2 problems with these, or a problem with each. The first problem, you can just load your driver before you run the game, bypassing this sort of runtime prevention. Second, if you're going to scan through all of sort of suspect kernel memory and sort of try and signature scan, this is an incredibly slow and sort of performance-intensive process. And also, neither of them can really detect something like a 0-day or code that's been mapped either through UEFI or maybe a DMA card. So some anti-cheats have sort of started using arcane measures. In this case, we're going to investigate Valorant and Riot Vanguard. To look at Vanguard's kernel defense, we first need to find their entry mechanism. In this case, it's inline hooks. So we'll cast a magic spell to find hooks. Once we've done this, we'll find 2 interesting hooks in the Vanguard driver, 2 targets, and 2 detours. If you look at the code at the bottom here, you'll see a detour and then a NOP slide. This is where Vanguard has replaced the normal kernel code. If we have a look at what these functions are, we find the first is the Windows page fault handler. This handles things like bad access, page protection violations, and importantly here, execution from no execute pages. The second function is a bit more confusing. It's a software trap handler. It's quite obscure, and it's normally used for deferred kernel work. So what's the link? To find that, we're going to have a little dig first into the page fault handler. If we look at the hook, where it jumps to, we find this. For those of you who don't speak assembly, it's quite simple. If the interrupt has come from the kernel, if it's been caused by an NX execution, and the interrupt request level is correct, we're going to jump to a custom handler passing the faulting address and the error code. So the handler is now set up to catch no execute page faults from the kernel. Why? Malicious code is sort of often mapped into two spaces. These are specifically spaces where it won't be written back to the disk. So we have like a nice safe space for your custom driver, your cheat, your malware to run. What Vanguard does is on game boot, or whenever this hook is loaded, it sets these suspect pages to no execute. Here we can see the PPE level, which is you'll only get 1 or 2 of these pages per system. So it's really quick to quickly write no execute. You don't have to scan through all page. Fantastic. So from now on, any execution in these areas will cause a trap. A trap that goes straight back to our hook. So we've installed our hook. We've sprayed NX on areas we think cheats or malware might be. Any execution from these non-paged pools will then throw an exception. This will get caught by our custom handler. And because we're piggybacking the Windows handler here, we're getting the address of the fault delivered straight to us. We can then analyze, respond. In the case of anti-cheats, they'll send it back to their server and analyze it. If you were an EDR system, you could just blue screen the machine right away, do whatever you want. So we tried to replicate this. Install a simple inline hook on the Windows page fault handler, just return back, don't do anything special. But we get a blue screen. What's happened here is Windows kernel patch protection has killed our machine. Why has it done this? This is where we find the link. PatchGuard. Windows PatchGuard protects critical kernel structures and functions in Windows. It's a heavily obfuscated system. It hides itself by piggybacking legitimate kernel entry points. And in this case, it's killed our system when we try and mess with the page fault handler. And what we find is the second hook is one entry point of Windows PatchGuard. So here we find our link. The page fault handler is a core function protected by Windows kernel patch protection. And software interrupt handler is being piggybacked by Windows PatchGuard in order to enter. So to turn off PatchGuard here, what Vanguard have done, it's very simple. They've just added another function call to the software handler. And all this does is go to HAL perform end of interrupt and say, no, thank you, I'm done interrupting. Return back to where you came from. So they've essentially shushed that entry point for kernel PatchGuard. They do that, and they do a couple of other things. They also mute currently running PatchGuard contexts by queuing infinite wait times. If you look on the slide there, you see FFFFFF. That's the wait time on the system thread running PatchGuard. And you can see Vanguard have their fingers in that kernel stack. It also corrupts deferred procedure call structures, breaking PatchGuard's deferred execution and checks. So to recap what's happened, we've installed a no-execute net on suspect areas of memory, and we've added a hook to catch any execution. We've turned off Windows patch protection because it's pesky and gets in the way, and therefore mapped code falls straight into the net for the anti-cheat to analyze.
Let's talk about another defense, software diversification. And this one is really cool in my opinion, because as academics, we're talking about software diversification since years and years and years, but beyond like address space layout randomization and position-independent executables, we never really got far with that. And now we see this deployed in anti-cheats. So let's wrap up what really is the issue. Cheats and exploits alike usually do rely on offsets and pointer paths when doing their malicious activity. So a cheat would, against a given game, check the module base of the different object files and then go through the different offsets, checks different pointers, and eventually would find an interesting value it wants to hijack or visualize to the player. In this example, it's, for instance, the health of an enemy, could also be the location or similar. Now, when a game is updated, these offsets usually change, right? Because the program is completely recompiled, things are different, and that the same offset from before may not be something completely different. If we're lucky, for instance, cat pictures. So what happened here is, or what happens here usually is that cheat developers would, for each game update, release a new version of their cheat to fix the offset so that it can work as before. So this benign game update process is obviously introducing some more work for cheat developers and hence drives the attack costs for cheaters higher. Now, what if we could do this just all the time for every single player, right? If we don't only have updates once the game is updated, but each player has a different version of the game. And there is one anti-cheat out there, or one anti-cheat system which deploys this, and this is the QB system of Rainbow Six Siege. Now, the process here is that not each player really has its own unique software build, but there are more different pools of build. In this example, we have 7 different pools, but it can be arbitrarily more. At the beginning, so when the player gets the game and downloads it, each client, each player has the same build of the game. Then the first time a multiplayer game is started, the player will need to download a new build or a new version, a new patch for the game. And this patching process is repeated at regular intervals, and each pool will receive a different patch set. So what is in these patches? What is in the updates? What changes? First of all, the offsets, right? Like this is what really makes it harder to just have one cheat working. If we have a lot of different game builds with different offsets, we would in theory need a lot of different cheats for this game. Another thing which changes are encryption keys. Part of the games are encrypted and are only decrypted during runtime, and different builds would use different keys. And also the obfuscation techniques are slightly changed, or the obfuscation results, so different parts of the binary would be in different places, instruction would be aligned differently. So obfuscation is different across these different builds. For a cheat developer, this has 2 main effects. First, we need to develop, as cheat developer, a unique cheat per unique build of a game, which is just time consuming, right? If we say there are 8 different pools of games, we would suddenly need to develop and maintain 8 different cheats and then repeat fixing the offsets on any update cycle. The other method or the other effect is that as a cheat developer, one could try to signature scan and use like dynamic techniques to find the offset during runtime. This is of course also time consuming and a little bit more difficult. It's not impossible, and game cheats do it, but it drives up the cost and effort for an attacker. And one interesting thing here, right, we are talking all the time about cheats, but this applies the same for regular attacks and exploits. If we are able to shuffle binaries and give different binaries to different people, there's not one exploit which can rely on the very same offsets. Let's move on to the next defense.
Okay, so next I want to talk about rogue hardware. Some of the most powerful attacks against any system is to use some bad hardware. If the attacker has physical access to the machine, a whole range of powerful attacks are possible. So first, a quick primer on Windows memory. An application will have a virtual memory address space, and this will be mapped to physical addresses by a unit called the MMU. This allows the application to read and write memory. Also on your laptop, on your machine, you'll have a certain number of devices, network cards, that kind of thing, connected by the PCI bus. Again, the applications can talk to these devices, send network data, receive network data. Now, to make things much more efficient, there's a way where the devices can bypass the kernel entirely and talk directly to the memory. Now, importantly, this bypasses the kernel, so it bypasses all of the defenses we've talked about. This means that a malicious device on some systems can access the memory directly, bypassing the anti-cheat or any antivirus, leading to a range of powerful attacks. On Windows 10, you can bypass the lock screen entirely. If an attacker has hardware access to your device, it's no longer safe. The thunderclap attacks showed how to do this with a USB-C device, which made it a very dangerous attack for anyone plugging in a device. It also breaks the security model of a lot of cloud providers. A cloud provider can easily dump out your entire system, no matter what protections you run. And of course, it's used for video game cheats as well. To use it for a video game cheat, the cheater will plug in one of these cards to their desktop PC, which will connect to a second machine which runs the cheat code. This means that all of the cheat code is not running on the same game as the anti-cheat, making it very hard to detect. The cheat might, for instance, interrogate the memory, work out the position of enemy players, and then it will use a device which fuses the HDMI connections to display enemy positions and more information on the screen. It might also simulate mouse movements. This makes the cheat incredibly hard to detect, but that direct memory access for malicious hardware must be registered with the kernel in order to function, which gives anti-cheats a way to counter this. So this is what a direct memory access card looks like. And the anti-cheat will scan all of the hardware devices on the machine and collect their metadata, their serial numbers, their identities. If it finds a direct memory access card, the kernel instructs the IRMMU to disable it. The kernel can always disable hardware devices. So anything which looks like a direct memory access card is instantly disabled by the anti-cheat. In response, these cards have got sneaky. They've pretended to be legitimate cards. They've reconfigured themselves to say, I'm a network card, for instance. But the anti-cheats will dig deeper. They will collect all of the configuration data. They'll check the registers are behaving correctly, and they'll check the interrupts. They'll actually try to say, can I interrupt it like an actual device? Even further, if it's reporting to be a network card, for instance, the anti-cheat will actually try and send some data on it to use it as a network card, and if it doesn't function as it should, it disables it. Now, this works as well with faulty hardware as well, right? If you've got an unused network card, disabling it is fine. So this provides some of the very best defenses we've seen against rogue hardware. Very little stops these attacks. As far as I've seen, anti-cheats are the best way to protect your machine from rogue hardware.
Right, looking at the last defense, we're going to learn how to hide memory. Memory protection, info stealing, it is probably one of the biggest problems in cybersecurity. Easy Anti-Cheat and Vanguard both have cool ways of making important values and memory significantly harder to find. We're going to present Vanguard's because I think it's very neat. As a bit of a primer, each Windows process runs in its own virtual address space. This means one process can't mess with another, and if a process crashes, it crashes in isolation. Control register 3 holds the page map address, which tells the processor where it's executing. Switching processes involves loading a new value into control register 3, and we're now working in a different address space. Write Vanguard hooks the context switch just after it happens here, and it checks a few things. Based off these checks, it then rewrites CR3. What's it checking? Again, if you don't speak assembly, that's fine. It first checks if the new address space is for the game Valorant. It checks if the new thread we're switching to belongs to Valorant. And finally, it checks if the thread belongs to a predefined allow list. If all of these three things are true, it then jumps to a custom handler, and depending on the result of that, will switch to a secret CR3 value. So to have a look at this, a context switch occurs. Our new process is Valorant, and our new thread is allow listed. CR3 is shifted to point at a different address space entirely. If we have a look at what that might be, the normal Valorant address space, we'll find things like, is the game paused, some status stuff, some info on your player. If we look at the secret address space, Valorant 2.0, we will find extra values such as enemy locations. By doing this, what we've done is we have put all of our secret values, things we want to protect, in a copy of the address space somewhere else in the kernel. To find this is non-trivial. You're going to have to search through all of kernel space or reverse engineer the hook. To recap, we're augmenting the scheduling system, and we're cloning our paging map to redirect good threads to a completely different process address space that we control, that we can put our secret values, our passwords, et cetera, in. and we've created an invisibility cloak for memory. Any process that tries to attach normally to Valorant will not see important values at all. We're going to pass over to Tom to have a look at the impacts of anti-cheats.
OK, so we've presented a lot of defense methods. We wanted to actually say, do these work? Are these actually effective? So to do this, we went back to our data set of all these cheat-selling websites. We looked at the strength of all the anti-cheats, the availability, the price. And first, looking at availability. Valorant, which had the most of these features, we saw uptime of the cheats at about 50%. So about half the time, people were paying for cheats which didn't work. Some would only stay up for days. Counter-Strike, which had the least of these defenses, you could see most cheats were up most of the time. So this gives us strong evidence that these anti-cheat methods really do stop attacks. They make it much harder. They massively increase the difficulty for the attacker. This is the games we mentioned ranked by the number of these defenses they employ, by the strength of the anti-cheat. This line is the uptime of the cheats. And as we can see, there's a pretty clear correlation with the weaker cheats having the weaker anti-cheats having much more effective cheats. And more importantly, this is the price of the cheat. And there's a very clear pattern where strong anti-cheats massively increase the price by an order of magnitude. So these defenses literally increase the price for the attacker, providing strong evidence that these defense methods really do work. We controlled for other factors such as game popularity and anything else we could think of that didn't affect the price of the cheat. The price of the cheat purely depends on the number of defenses employed. So this is strong evidence these defense methods really do work.
So with all of this in mind, we want to look a little bit what we think what the next battleground is going to be for cheats and anti-cheats, right? We see the Windows kernel as this harsh planet, but where is the journey going to go next? And we believe it will look something like this. So we had cheats and anti-cheats moving from user mode to the kernel, and we believe in the future cheats and anti-cheats will likely move more and more towards the hypervisor. Now, we are no fortune tellers. We make educated guesses based on the information we have. And in this case, the information we have is cheats show first evidences that they're relying on hypervisor features. We see here one particular cheat from ring-1, which says it's for Intel-only CPUs, so it must be related to the hypervisor architecture, and also that it's helping a bit with Windows 10 and Windows 11. Then we also see the anti-cheats, an anti-cheat developer starting to make comments about the hypervisor, right? We see comments from anti-cheat developers which are saying, if they start requiring virtualization-based security to be on, so they will be Windows, we will leverage those features that protect Windows for us. And last, of course, it's also us in the middle. We did first experiments with hypervisor-based features, and as we saw earlier, some anti-cheats may already crash our attempts right here. So we do see, or we do think, in the hypervisor, there will be the cheats and anti-cheats of the future likely to be found. Let's wrap up the talk and come to our takeaways. First of all, we want to really recap that we saw a lot of cool defenses. Anti-cheats have really a treasure chest of defenses. We just show a couple of them in our talk. We talked about how we will detect unsigned code in the kernel, partially with stronger protections than what Windows itself provides. We saw how we can stop rogue hardware attacks from anti-cheats and DMA attacks. We did see a practical software diversification scheme, and we also discussed about a cloak for invisibility of memory. Now, the final takeaways for our talk are anti-cheats implement some of the best defenses out there. We should really get inspiration from there. Then, a system is never as safe as when a user is playing Fortnite or Valorant. These games with strong anti-cheats do effectively help the security of an overall system. And last, if game developers can implement these defenses, so can we as developers, right? Let's try to take some of the things we learned here and bring it to more software to make more software secure. Thank you. That was our talk. We're happy to take any questions, and you can also find more information on a website we're currently building up about our research on games. Thank you.